Okay, going to do a little quick review of the moon notes from Sellers' class. Obviously, notes are posted online as well, but just thought I'd give a quick review. Lunar phases, first thing you should probably know, is something you've probably learned since elementary school. Um, Lunar phases are important in that there are certain phases where eclipses can happen, and you need to kind of know that. As far as knowing in particular shape as to whether this is the waning or waxing crescent, I won't be asking that on the test. That's a little bit too specific. Um, but to wax means to gain light, and wane means to go away from it. So if you're starting at the new moon phase, we don't see anything because it's not nighttime or facing the moon here. So you got to always remember we're on the back side of the planet compared to the sun over here. So goes new moon waxing, starting to gain some light, right? So you only see a sliver here. Here you see half of the moon, which is only known as the first quarter. Then it goes waxing gibbous. Full moon, which is the full half of the lit surface that we see. Then from full moon, it starts to wane away or to kind of fade away. So waning gibbous is almost a full. Then you have the third quarter, which is opposite to the first quarter. And then you have the waning crescent. And then it goes back to the new moon. Known as the synodic month, takes 29.5 days to complete an entire cycle. I just mentioned all of this. The waxing is the gaining of light. Waning is to lose it. Feel free to stop the video if you feel the need. Phases come to impact eclipses in a great deal. So we're going to talk about how these eclipses occur and how moon phases play a part of that. So to eclipse something means to hide it, right? To shadow or to hide it. In a lunar eclipse, the moon is eclipsed or hidden, right? It never really goes away. It just kind of gets this reddish tint. We talked about why that was in class, and if you have a question, check out the eclipse video I posted. Must be in the full phase for this to happen. It has to be behind Earth, in Earth's shadow. So, inversely, with solar eclipse, the sun is eclipsed, and this must be in the new phase. So, you flip back to this diagram, you can kind of see what's going on here. For a solar eclipse, right, sun over here, it has to be in the new moon phase for this to cause a shadow to cast upon the Earth. Inversely, it has to be in the full moon or behind the Earth to be in the shadow. Doesn't cause an eclipse every time. I should mention that. Because the moon is a little off kilter from the planet, about 5 degrees. So it does not typically hit us. When a solar eclipse, I should probably correct that to say solar eclipse. You have two darker regions. You have what's called the umbra, which is the darkest region. It's a very small section. If this entire green circle is a shadow, the umbra would be the very, very tiny part right here that's just the darkest part. It's very small, about 2 miles wide, and it's what goes through what's called totality. The much larger but not as dark section is known as the penumbra. Annular eclipse occurs because the moon's orbit's elliptical. Sometimes it's closer, sometimes it's further away. If this is the case, then it doesn't cover the entire surface of the sun, and you have like what's technically called a partial eclipse, but because it does cover the entire surface almost, right, we determined that it's called, or we've given its own name known as the annular eclipse. I mentioned this a minute ago about the eclipse geometry and why that doesn't always align. So, Let's talk about tides. Tides are caused by what's called gravitational deformation, which is the reshaping of a body due to gravitational tugging. Now, in our case, obviously the bodies are Earth and the Moon. So, this causes the planet to bulge, and it kind of squeezes the planet up to 3%. So as the Moon pulls at the Earth, I said water is the most affected. So you have two different high tides and two different low tides. Low tides occur on the areas that are away from the Moon or opposite to that. So if you look in this position here, right, this is a high tide here because it's pulling it off, and as it kind of bulges the entire planet, right, squeezes it, if you will, and this kind of gets pushed backwards, kind of like a balloon, as well as this gets pushed this way. Well, then these two places get a little bit smaller. So as the Earth rotates much more rapidly than the Moon does, as this moves around here, it'll be where it is now low tide, it'll be high tide, and then over here it'll be low tide again, and over here it'll be high tide again. So this is the reason you have two high tides and two low tides. A great video I posted as well that kind of explains that with motion, which I would advise you to watch. There are also spring and neap tides, and spring and neap tides are when you have a spring tide. Let's just start with that. It's when you have an extremely high, a high tide and a high low tide, and this is caused by gravitational influence that is combined from the Moon and the Sun. So on this side you have, let's just look up here, at the full moon phase, this only occurs at full new moon. So at the full moon, the Moon is pulling this way, and the Sun, right, which still has a lot of gravitational influence on our planet, the Sun is pulling in this direction. So you have really, really high tides and low tides as well. Now, the new moon phase does the same thing, but this time you have this plus this, and just kind of deforms it to pull water out a little bit harder this way. Right. Inversely, you have in the first and third quarter phase, you have gravitational almost canceling out. You still have tides because the Moon is really close, but because the Sun is pulling this way and the Moon is pulling this way, right, the high tides won't be as high. It's known as neap tides. Now the Moon has another interesting fact to it. It's what we call tidally locked to the Earth in a gravitational way. And as a result of this, it rotates and revolves at exactly the same rate, making it a synchronous orbit. So it does rotate every 29.5 days, but it also revolves at that same rate. I like this diagram because it shows the little man here, and as the little man goes around the Earth, right, in its revolution, if the Moon did not rotate, right, then the little man would always be facing the same direction, which would be up and down, up and down, up and down, up and down, up and down. He's not facing up and down all the time. I'm saying relative to this. And as a result, he's always facing the Earth, and that's because it's tidally locked. Four major theories on how the Moon came about. First idea is the sister theory. This is the idea that the Moon formed at the same time that the Earth formed. If that's the case, then the Moon should be compositionally the same as the Earth. Lunar missions, especially the Apollo missions, kind of revealed that that was not the case. It's compositionally very different. It's made of some of the same rocks as Earth, but that's to be expected. But when I say compositionally, I mean really the core regions and the mantle should be proportionally the same as the planet Earth, and it's not. So we no longer believe that it was formed at the same time. Now, another theory was the capture theory. Now this works with planets that are really large, like Jupiter and Saturn, but it can capture a small body like an asteroid or even a small moon because it has such a great amount of gravity. It can kind of perturb an orbit enough to where it actually will capture it and kind of make it fall into an orbit around that planet. The Earth and Moon are not going to work that way because the Moon is so large compared to the Earth. The Moon is a quarter the size of the planet Earth, so Earth does not have enough gravity to slow something down and kind of capture it within an orbit. This is the most widely believed theory in the 1800s. This is what's called the daughter theory, and this is the idea that when Earth was molten, when it was really, really young, it was spinning so fast that a large glob flung off of it. It's believed to be in what is now the Pacific Ocean basin. This doesn't work in computer models because in order for that glob to spin...
Good afternoon.
I got cut off by the announcements, but the final theory is the impact theory. This is the most widely believed theory at the time. Computer models show it, and that's what this is showing over here. A planet kind of grazes it, gets ripped apart. This planet's about 50% the size of Earth, about the size of Mars. When it gets ripped apart, we steal most of the iron. It goes inside of our planet, which makes our core larger, makes our magnetosphere larger and stronger. And then it kind of forms out this leftover little junk out here is the Moon. Now, compositionally, this really works out when we get to the lunar modules or the lunar missions. Now, like I was just saying, when the Apollo missions landed, they had these the legs in the lander was left behind, and these landers had seismographs in them. So we've been tracking moonquakes, and we're able to study the interior based off of these little moonquakes. Now they're not strong earthquakes like we have here because Earth is a lot more geologically active, but there is like tremors, and we get to study the small vibrations through the moon in order to study the interior. Now this is kind of painted a map of something like this, right? It's mostly rocky. Asthenosphere is kind of a warmer layer of the mantle, if you will, right? And this is all solid here, and there's a core region here. This is my idea of the lander, right? And this blasts off. I showed a video in class. This blasts off and regains the orbit or reconnects with the orbiter, leaving the legs behind. Now, the seismographs have revealed that the Moon's core is compositionally much smaller, or proportionally much smaller. Compositionally, it's probably the same stuff, but this helps to disprove the sister theory, because if the planet Earth was this big and had a core of this X amount, right, then the Moon, if born at the same time, remember sister theory, should have a larger core proportionally, and it doesn't. This also helps to support the impact theory, which is the idea that we ripped off a large amount of the metal from this body that is now the Moon. So as it was colliding in, we stole a bunch of the metal into our core. Couple of physical properties about the Moon. It's a quarter the size of Earth. It has 1/6 the gravity of Earth, which is why astronauts are able to jump around so easily. It's also why the lunar module is able to escape the Moon's gravity so easily, right? It doesn't take as much force to get off the Moon, which is a great thing. It definitely does not have an atmosphere. It just has way too low of a mass in order to hold on to gases. So the interior is a small iron core, like I was pointing out a minute ago. It gives it a really weak magnetosphere, or magnetism, about 1/1000th of Earth's. Which is very Sajad-like, which is not strong. Mantle material is now solid, and we believe it to be no longer volcanic. Lunar surface. Let's talk about what a crater is. This is probably the most recognizable lunar surface feature. Crater comes from the Greek word meaning bowl. It's a depression caused by a meteorite impact. It has several different parts to it, including the rim, which is basically the lip of the crater. And then the ejecta is the material blown out, surrounds the crater after the impact. I'll point these things out on this slide here. Here you can see the crater, right? This goes A, B, C, D, right? Boom, 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 boom. So in D, you have the crater itself as the bowl, right? The rim is the very lip of it. The ejecta is the stuff that is thrown out in these different spots here. So it forms what's called the ejecta blanket. So in this case, this would be the crater, the rim, and the ejecta blanket. The darker regions on the moon were named Maria by Galileo, and he named these depressions or darker regions of the moon. He named them after oceans or seas, as that's what he thought they really were. He thought it was some kind of ocean on the moon, right? And that's not crazy to think that, because our planet has oceans, and maybe that one does too. And he had a very weak telescope, so that's not as crazy as an idea as you think it would be. So we kept that name, and we now name other features on the moon the sea, like the Sea of Storms and the Sea of Tranquility and so forth. So what causes them? Well, large impact craters, when the moon was still volcanic and young, when they were colliding onto the planet or onto the moon, cracked the crust area or crust enough to where magma could leak from the still warm mantle underneath, and it filled up those depressions. And I like this diagram because it really shows it. So as these impact craters hit, they were large impact craters first of all, and they definitely crushed a bunch of the crustal material, and magma from the mantle area was able to seep in and fill it in with this dark igneous rock that we call basalt. So, and that's the reason these regions on the moon are darker today, because they're filled with basaltic lava. Moon's only form of erosion is what's called micrometeoroids, and micrometeoroids are basically sand grain or smaller pieces of space debris that are flying around at extremely high velocities, and this basically has a sandblasting effect upon the moon. It's not wind or water erosion, but look at this picture. You can kind of see how it just looks worn down, right? It's a great shot because some of these craters look to be almost eroded away from micrometeoroids. And these two lines here are caused by the lunar rover, which is this little guy here. Now, this has made most of the surface of the moon covered with what we define as regolith, right? Regolith is a fine powdery surface that's caused by ejecta from impact craters and the erosion from micrometeoroids, both of which the moon gets lots of, right? Especially micrometeoroids. It's just on Earth, we don't have micrometeoroids hitting because they burn up in the atmosphere. Now, they actually do come into that planet a good bit, but they never make it to the ground. And this, of course, led to the very famous footprint from Neil Armstrong. It's kind of the consistency of flour or ashes from a campfire. It's just this super fine, powdery kind of rocky soil, right? And used to be rocks, and it's basically just been pulverized again and again and again and again and again, and it just makes this fine powder. Consistency closest to like flour. And I think that's it. All right, see you in class.